Gbetondji Dovonon, second year now, PhD student at University College, London. And yeah, I'm going to be talking about the long-run behavior of multi-fidelity Bayesian optimization, right? So let's first start by the context in which this project was done. So it was done at Matterhorn Studio, obviously. Yeah, here's a good picture of all of us. Yeah, I think, yeah, that's all of us, right? Yeah, nice little group. So funded by an Innovate UK grant. And as part of this project, I was working on multi-fidelity Bayesian optimization, right? I started by doing a review of this new field because unlike Bayesian optimization that's been there for quite some time in this well-studied, multi-fidelity Bayesian optimization as a subfield of Bayesian optimization is not really that clearly defined. There's not much work done on it, and there's not even any reviews or surveys of the field that's out there and can serve as reference point for people starting in the field. So at first we thought we would start by filling in when it comes to that need, which would be very useful. And then as we started doing that, we found a failure case that we decided to analyze, a failure case of multi-fidelity Bayesian optimization, which is the long run, right? The long run behavior. So let's start with the review of multi-fidelity Bayesian optimization. And before we start talking about multi-fidelity Bayesian optimization, we need to talk about Bayesian optimization. I guess most of us are familiar with it here, but we can just go over some principles quickly. So here, this is what a typical Bayesian optimization process looks like, right? So you have the true function in orange, which is what we are trying to either minimize or maximize. It depends on what exactly we are doing, right? So I guess here we are trying to maximize this true function. There's global maxima, there's a few local maxima, right? So we use a Gaussian process to serve as surrogates to kind of like approximate this function based on the data available so far. And the nice thing about the Gaussian process is that for each point, it gives us a confidence interval that we can then put in our acquisition function to tell us what should be the next point to evaluate, right? And based on that, we iteratively evaluate points until we find the global maximum, right? Now, why should we use multi-fidelity Bayesian optimization, right? Bayesian optimization helps us minimize or basically optimize expensive functions. We iteratively find new points to evaluate, but an irreducible part of the total cost is the cost of each evaluation. And one would think that that's just how it is, right? But no, that is not just how it is, right? And that's where multi-fidelity Bayesian optimization comes in, because we now have access to lower fidelities that are both less costly and less accurate. And multi-fidelity Bayesian optimization tells us how to use them to end up optimizing the function while incurring less cost. So multi-fidelity Bayesian optimization can be done in multiple different ways that we categorize in the context of our review in 3 categories, right? The first one is an extra output. So you have a Gaussian process that will have an additional output for the fidelity and is used with a cost-adaptive acquisition function, right? So here you can use basically the Gaussian process will select both the fidelity and the point to evaluate, right? And then if you want to evaluate a specific fidelity, you can just constrain the output of your GP to that specific fidelity, right? That's one of the main methods that's being used currently. It works well for continuous fidelities, can well for discrete fidelities also. And yeah, that's the main method right now. Another method that's actually a bit older, but was not explored as extensively is instead of an extra output, having an extra input. So an additional input for the fidelity is added to the parameters of your function, right? And then you can select the fidelity you want to evaluate and just set that extra input to that, right? And then the last method, that's actually the one that's used the most, even though it's not exactly considered a multi-fidelity method in most cases, is just a whole bunch of heuristics. They are varied, they can really be anything. And an example of such heuristics is successive halving that's used that's used a lot for hyperparameter optimization, right? So successive halving in the case of hyperparameter optimization can look like having a specific budget. So that can be training for 100 epochs, for instance, right? And instead of starting with a total budget of 100 epochs, you decide to have your lower fidelity be at first 1 epoch. So you train 100 different hyperparameter settings for 1 epoch, then you halve the population and double the budget, right? So the fidelity is increasing and the population or the size of the total settings you are evaluating is being halved. So yeah, that's why it's named successive halving. There's quite a lot of different heuristics like that, but there's not a single way of describing all of them, right? And they're quite varied. So now we get to the next part, the long-run behavior. Now that we've looked at multi-fidelity methods, here when we are talking about the long-run behavior, it's going to be mostly the first category of methods, right? The one here, the one with the multiple outputs, right? Now, what triggered that? While looking for papers on multi-fidelity Bayesian optimization, we found this paper here, multi-fidelity Bayesian optimization with unreliable sources, right? Quite an interesting paper that actually looks at another failure mode of multi-fidelity Bayesian optimization, which is failure to not account for fidelities that are just too unreliable, right? In most cases, you assume that the fidelities are at least a bit reliable, but what happens when they're like almost completely unreliable? So this paper tackles that. But in this paper, they have this very interesting plot here, right? When you can see the maximum entropy search algorithm, it's single fidelity variant and it's multi-fidelity variant. The interesting thing you will notice on this plot is that the multi-fidelity variant is much better until a budget of approximately 25. Then the single fidelity method is better, right? Then that highlights a possible issue in terms of the long-run performance of the multi-fidelity methods, right? What happens when the budget available becomes increases, right? And that's the issue that we decided to look at and analyze. And we decided to first try to reproduce this issue. So here is, once again, MES. In red, you have the multi-fidelity variant, and in blue, you have the single fidelity variant, right? For the Hartman problem, right? For the Hartman problem, Hartman 6D environment, you see that the multi-fidelity one performs better until a budget of approximately 50. Then the single fidelity one starts outperforming it, right? And on another one, which is XGB, the first plot we made stopped at a budget of 100, where the multi-fidelity one was still outperforming it. But when you extend the budget all the way to 500, you see that on the long run, once again, the single fidelity methods outperforms it, right? So yeah, that's basically the issue we decided to highlight in our workshop paper, right? That multi-fidelity methods, though they perform well in the low budget setting, might have issues on the long run. And yeah, now we are looking at extending this plot to more environments, right? What would happen if you have a function that has just one global minima and no local minima is completely smooth? What happens in this case? What happens when you have multiple minimas? So we want to evaluate with more functions, with different settings, and also with different algorithms, because so far all our plots are limited to the maximum entropy search. The next experiments that we are going to run will involve knowledge gradient and its multi-fidelity variant, and potentially one or two more algorithms. And yeah, that's it.
That's great, Gbetondji. Thank you so much. I think that was quite interesting, a good summary of the work we've done over the last 6 months. Is there any question? I can only see Rory. Rory, do you have any questions on that?
Yeah, I think the question for me is, what characteristics of problem are going to make that crossover point earlier or later? Because in your two examples, there's quite a big difference in the amount of budget before you get a crossover.
Just to make sure I understand your question, you're asking what characteristics are going to determine the point for the crossover, right?
Yeah.
Basically, how soon does it crossover? That's an interesting question to which we do not have an answer yet, but that's something we are looking at, right? And potentially running more experiments is going to help us answer this question, right? And we do not even know yet if that crossover point exists for every single environment or for every single algorithm. So far, we've only reproduced the issue on two environments. This one is XGB, and this one is Hartman. So yes, finding trends in terms of how soon the crossover point exists, if it exists at all, or even theoretical guarantees in terms of whether that crossover point exists, how to avoid it, things we are looking at.
And is that happening because it's oversampling the lower fidelity, or what's actually going on when you get the crossover?
Actually, looking at the fidelities that have been sampled, one pattern for most of the multi-fidelity runs is that early on it samples the lower fidelities a lot, and then starts sampling the higher fidelities more going on, right? But then for some reason, even when it starts sampling the higher fidelity, so for instance, on Hartman, I've had a look at it, I think from even before that, around 40, it starts sampling almost exclusively the highest fidelity, right? But then the performance does not improve that much after that point, right? Even though it's relying mostly on the higher fidelities. So my guess would be that the lower fidelities, though they are useful, the inaccuracy that they add to the data kind of mess up the predictions of the GP on the long run and make it evaluate points that are just not that useful after that, right? Like some sort of error propagation thing, right? It could also be that it's stuck on local minima for some reason, right? So that's also one of the reasons why we need to evaluate it on malfunctions, functions with different sort of curves, right? Some with more local minima, some with just one global minima, just one minima, right?
So the single fidelity is sampling the highest fidelity out of the multi-fidelity. Is that, sorry, I know that's a really bad sentence, but is that
Yeah, the
correct?
single fidelity is only sampling the highest fidelity.
So that means they're both sampling the same fidelity from what you're saying, but because of the errors earlier on.
Yeah, after a certain point, they're both sampling the same fidelity.
Right.
Most of the time.
So it should basically start ignoring the old lower fidelity data at some point. Or like, if you're like a human, that's what you do. Maybe that.
Yes, I guess so. Yeah, but I'm not entirely sure how exactly that happens though, because yeah, I would still need to do a few more experiments to validate my expectations. But yes, I assume that if at some point it starts ignoring the data from the lower fidelities or somehow correcting that, because I guess one issue that could still happen is if you just get rid of the data from the lower fidelities, then you also get rid of the knowledge that even got it to that point, right? What happens if it then starts sampling back at those lower fidelities?
Yeah, I think that discussion captures pretty much what we've been thinking about so far. So I guess my two bits is that obviously whatever test function we use, the closer that is to reality, the more this behavior we probably will observe in reality. But like strictly speaking, we don't know, for example, with an alloy, whether the Hartman 6D is like an alloy behaves. We just don't know that. We can only guess that. And so I guess from the empirical perspective, Gbetondji is running different test functions to see if that happens with all of them or just some of them. And that informs then a theoretical inquiry of like, why does that happen? What's the statistical argument here? And so the only thing, apart from what Gbetondji already listed, that I like to apply here is that there's no free lunch theorem. So yes, in the beginning with multi-fidelity, we sample a whole bunch of low fidelities that are cheap, but like I guess they come back to haunt us at a later stage with being stuck in a local optima or like being just too coarse and approximate and then misleading the querying of the single fidelity. So that's that. But I think over the next couple of days we're updating the workshop paper anyway, so that discussion is going to be there as well to cover all of these hypotheses. And yeah, I think that's it so far. So then the answer to the question of can you predict when the crossover point is, well, you can if you know what exactly the test function is, because you can just run it. But of course with materials we don't know what the material space looks like, what the surfaces are. So it's kind of a holy grail to be able to predict where the crossover point would be, because by the nature of the problem, we just don't know where that is. But I think it's incredibly relevant to know that it exists, at least, because if you just put all your money into multi-fidelity Bayesian optimization, but you do run a lot of experiments, you do need to answer the question of, is this actually going to be better in the long term than single fidelity? All right. So that was a good presentation. Gbetondji, I really liked how you introduced that. And I think there's one more plot as well with the HPO bench. I think that's in the workshop paper, right?
Yes.
So this is not just a plot that Gbetondji made or a plot that's available in the unreliable information sources paper. There's also other plots that show this behavior. But I think with this work, we kind of seem to be the first ones to be looking really deeper into the issue of this. And so we're just really hoping to see what people say at the workshop in 2 weeks already. And so hopefully we can update the archive then with what people say. But that sums it up really. Anything else from you, Gbetondji?
No, that's it.
Sounds good. All right. Well, thanks for coming. I'm going to stop the recording here.